Welcome everybody to this new week of the information retrieval course. So I'm going to finish off what we started last week, which is the section called term vocabulary. And then we'll move on to the next part, which is about mostly spell checking and looking up the terms. So where were we? What have we done so far? Well, last week we looked at a lot of languages. And the week before, you might remember that we looked at Boolean queries. So just like SQL is the language for relational databases, Boolean querying is one of the languages for unstructured data querying. So now I'm going to continue with a different kind of query language, which is called phrase search. Phrase search. So when you type a query under a search engine, for example, Google, can be also, maybe you like Bing, you like DuckDuckGo, there's plenty others, right? But let's just use this one. So you type your term in your terms in a natural fashion. So this might be interpreted, for example, as a Boolean query, right? So it looks for the pages that have ETH and that have Zurich. Right? But actually, you might be aware, or some of you might be aware, that you can also add quotes here and here in order to capture the fact that you really want ETH Zurich. That's called the phrase search. Phrase search, because now it's a sequence of words, and you really want these words to appear in that order and after each other. Another reason to put the quotes around the single words would be to require it, because Google might decide to ignore some of the words because it decides that it's less relevant. Then you can force by adding quotes. This is another way of using quotes. But the way I'm interested in today is for phrase search. It's when you have an entire phrase. Here there's only 2 words, but of course you can have a long phrase. It's particularly helpful when, for example, I'm sure you've been there, you have an error message that appears in your favorite language, and you copy paste it into Google, right? Who hasn't done that? And you probably notice that if you add quotes around it, it's better, because then it looks really for the exact error message that you're actually trying to fix, right? So this is called a phrase search, and this is the new part right there that did not belong to the querying, to the Boolean querying language, right? In the Boolean querying language, what we had were terms and then and or not. This is all we had. This is new. All right. So who thinks we can use our standard inverted index in order to solve this query?
Nobody's raising their hand.
Okay. Maybe for a good reason. Who thinks we cannot?
Well, most people, I think, have raised their hand now.
And why is that?
Okay, we have a volunteer.
Mm-hmm. Let's try the microphone. Let's try it out, since we have another hand microphone if you want.
So there you go.
We're missing the links between the words, so we've lost that information, and therefore we
exactly. Yeah, so we've lost information. Could you characterize the information we lost with more precise terms? The link that you mean.
Most importantly, the order. So, and which words are next to each other?
Exactly. It's the order of the words that we have lost. That's exactly it. You remember that 2 weeks ago, I showed you the set of words, bag of words, and list of words, right? So I told you we can abstract away. And in order to build this index, we abstracted away, and we picked the set of words, if you correctly remember. But the set of words, as you just said, lost the information on the order of the words. So it means that no matter how hard we try to use that structure, it just does not have the information on the order of ETH Zurich, because this is just lost. We threw it away. So there is no way we can use this, standard inverted index. Well, we could, right? We could still try to find the pages that have both ETH and Zurich, and then we do a post-processing phase where we search for the string ETH Zurich within the document, right? But it adds more work after looking at the index, right? But with Boolean queries, we did not need post-processing. We could directly use the standard inverted index. So indeed, we don't have any information on even the proximity here. We even wanted them next to each other, but we don't have any information on that. Who knows? Maybe, I don't know, document one is in both, but maybe in document one, there's ETH very early, and that's actually for the Ethereum cryptocurrency. And then maybe at the very end, there is something about Zurich, but maybe it's the insurance company, who knows, right? So we just have no way of knowing just looking at this index. But I have good news for you, is that we do have a solution. We just need to use a different index, right? There's not only one way to index the data. There's plenty of ways to index the data. So we have two ways to index the data in order to support phrase search. The first way is byword indices. It means that we look at two words next to each other with a sliding window like that, right? The other way is positional indices. It means that we are going to store the position in the document of every word, every term. So let's start with the byword indices, right? So I'll first do this one, and then once I'm done, I'll go into the positional index. Okay, so how does the byword index work? So here's a document. Right? I think I just copy pasted that from the ETH webpage, probably. So we build the index, but we are not going to build it in the same way. We are going to build it not by putting single words in there, the terms, what we call terms. We are not putting just one, we are putting two terms here. So you see, I'm taking help ETH, the first two tokens, which after all the post-processing we saw with the language lecture last week, gave us the term help and the term ETH. And then we have this pair of terms, two terms, and then the posting list. This here is the list of the documents that contain help followed by ETH. So this is not set of words, this is list of word semantics now. Right? So help ETH and then the postings list. Then we have ETH Zurich. So you see what's happening here. This is called a sliding window. It's a sliding window of size 2. I have two terms every time, and I just slide it pair by pair like this. So ETH Zurich, then Zurich 2, then 2 flexibly, then flexibly React, React 2, and so on and so on and so on. Right? And then of course it's not creating a new posting list every time. After a while, it will still be the same pairs, and then you actually start adding postings there. All right. So this here is a byword index. Right? Okay. So now, if I want to answer that query, you probably immediately see how that index is actually useful, because in that case, there's only two words, right? And by chance, we have a byword index, right? So this is actually perfect. So we have ETH Zurich, and we look for ETH Zurich. And there it is, you see? So ETH Zurich, and then we can just return these documents. And now you see, we don't need to post-process anything, because we are sure that all these documents right there, they do have ETH followed by Zurich, because this is how we build the index in the first place, right? Okay. Now, can anybody tell me how I can then answer this query right there using this byword index?
We have an answer. Let me just take the microphone. There we go.
Testing. Okay, so you can't answer it very well with these indices. You would have to do some brute force searches, so a 6-word index would be better.
Yes, that is a correct approach. You could, so you mentioned the 6-word index. So you could have built instead a 6-word index by having windows of 6 words. So that is absolutely a possible approach, 6-word indices. Now, can you find a way, even if it's a bit brute force, right? But can you find a way to, without building the 6-word index, by using this byword index right there, how would you use that index to answer this?
Sure. So you could find all of the documents that have all of the right parts here. I guess there would be 5 different parts that would all have to be there. And then once you have all of those, you could see if there's an intersection where, yeah, it has all of them.
That's it, right? So this intersection right there with the ends.
And then they would also have to be in a row, though.
Yes, exactly. We'll come to that, to being in a row. So for now, so as you said, the first idea is indeed to take the intersection. So we are going to find the documents that contain all of this. So we take these 5 postings lists in that case. And as you said, we indeed compute the intersection of this. And we are going to get plenty of documents that are the candidates for returning there. Now, the intersection right there. Now, there is an inconvenience to that. And let's dig a bit into that, because it has to do probably with what you meant with brute force. So there is a little bit of a challenge there. Can you see the challenge? Can I just return the documents on the intersection and be done? Anybody?
Yeah, go ahead.
So there could still be words in between the different bywords. For example, ETH something, ETH Zurich.
Yeah, there could still be entities between the bywords, as it were. And so that's the issue.
Absolutely. And by the way, we also look at the Zoom chat, right? Not in the lecture hall, not only in the lecture hall, I'm looking. So somebody, if you want to read Dan on the Zoom chat.
Yeah, I think that in the Zoom they said pretty much the same thing.
Yeah, the same thing, yeah. So we really monitor both sides. So wherever you are, we look for the questions. All right, so now coming to the answer you just gave. This is probably what you meant. Here's a potential document that could have been returned by this query, right? Because help ETH, check, ETH Zurich, check, ETH2, check, to flexibly check, and flexibly react there. So this document would actually come out of the intersection of the postings list. But is this document actually an answer to the original query? Is it? Is it not? Maybe the question is too easy because it's too obvious, but still I'm asking, is this document correct answer to this query?
I've seen some heads shake. No.
Okay, that's a very good sign. And I also see in the Zoom chat that there is a no, right? Okay, so indeed, this is not correct, right? Because this is what we call a false positive. It is a false positive. False positive, again, we might recall from what we said last time, it's positive because that's something we return, but we shouldn't have. That's why it's a false positive. So indeed, this is the issue that we have here. And I had a question for you in the Clicker app. I'm going to switch to right now. And here you go. So how do we solve that? How can we decrease the number of false positives with phrase queries? Oh, I'm showing the results. I didn't pay attention. Maybe I shouldn't show you your votes while you are voting. So let's look now. So Indeed, by using phrase indices with bigger tuples of words. And this actually was the suggestion that you've already been making earlier, right? The suggestion to use 6-word indices, right? So a 6-word index would indeed be a phrase index with bigger tuples of words. So this is in these solutions here, how you decrease the number of false positives with larger windows, larger tuples of words. Why is the third answer incorrect?
We have an answer in the room.
I was just wondering if false negatives was meant false positives, or is it on purpose? If it's on purpose, then it's wrong. That's my guess.
Yeah, so indeed, a false negative is a document that you wouldn't have returned, but you should have returned it, right? But the false negatives here cannot happen with the byword index, because the byword index gives you a superset of the documents you're looking for, but it will never omit to return a document that it should have. Right? So this is exactly why there are no false negatives in there from the first step. And of course, by doing the post filtering correctly, you will not have false negatives either, because you don't introduce any, right? Is it clear? So the important thing is, by using, let me phrase it formally. If you have a phrase search with n words, and you are using a k-word index with k strictly smaller than n, there can be false positives, but there cannot be false negatives. And you can indeed post-filter the results to get rid of the false positives, or you can increase k to make k equals to n, right? Equal to n, and then you solve the problem. All right. So now let me return to my slides. And if I prepared it correctly, we should land exactly where we were. If the next slide has nothing to do with what I'm saying, then it means I got it wrong. Okay, no, it doesn't. Okay, so now there is also an extra optimization we can do that's comparable to the stop words that we saw earlier, is that we can specifically tag the words right there, like for example, to, so, as to, you know, by trying to understand the grammatical structure of the sentence, you know, a noun, a verb, a preposition, and so on. And so we can try to only, you know, for example, you can specifically, you know, consider that you have an arbitrary number of irrelevant grammatical structures for our purpose. And then you can focus on the ones here marked as n, right? So you ignore to, you ignore so, you ignore as, you ignore to, and you focus just on the n, and then you only build the index based on the parts that you select, right? So this is one possible optimization. There are so many, right? There is no right or wrong. There are so many systems, but this is one more idea how you can fine tune the whole thing by tagging the parts of speech. Part of speech is the fancy word for saying noun, verb, preposition, adverb, adjective, and so on. That's called the parts of speech. All right. So byword indices. Now let's show you what happens if we increase k. So now not byword, but try words, right? So 3 words, then we say 3, 4, 5. So by instead of 2 is common, but then 3, 4, 5. We say 3 word indices that looks like this. So now you have LPTH Zurich, ETH Zurich 2, Zurich 2 flexibly React, and so on, right? And then you see it's the same idea here. I said n equals 6 and k equals 3, right? So the total size is 6, then there is 3. So of course we can still have false positives, but maybe there will be less now false positives. So if you increase k, if you increase the size of the window, then you make it less likely to have false positives. So here it's a 4-word index, and so on, right? All right, so now you see, if we come back to the earlier problem that we had a false positive here. That was a false positive to this query. But if I now take a 3-word, it's a tongue twister, right? A 3-word index like this, then you see that now the problem is gone, because Zurich to introduce here why did I underline this one? I'm not actually sure, but basically it's a true negative. This one is not going to get returned. Oh yes, I know, because Zurich to flexibly is not there, right? So Zurich to flexibly is neither here nor here. So this is why now it's going away. All right. So you see, now it's a true negative, and we solved the problem. Well, we didn't completely solve the problem. We would have to go all the way to a 6-word index to completely solve it, but we have less false positives than we had with a byword index. All right? Okay. So, but there is an inconvenience to building a 6-word index. Do you see it? Imagine I build a 6-word index now.
We need to store a lot more data for the index.
Yeah, absolutely. Absolutely. And on Zoom?
Well, we have one answer that says most posting lists will be very small.
Yeah.
And then another, can't find 2 words unless you keep it.
Oh, that's a good point as well. Yeah. So all right. So the first one is indeed correct that the problem with a 6-word index or larger values is the exponential increase. So the size of the vocabulary, so the total number of posting lists, is going to be a power of the number of terms. So it's terms to the power of, that would be k. I called it k earlier, but that's basically if we go all the way to the size of the query, then that's number of terms to the power of n. This is enormous. This is an exponential explosion, and I think you've visited enough lectures of algorithms and complexity to not like exponential stuff, right? So this is indeed a problem. The other remark on Zoom that most posting lists will be very small is a consequence of that. Is that indeed, if you stretch your standard inverted index by having many more terms or tuples of terms, then it will squeeze its breadth, right? So what is going to happen is that indeed the posting lists are going to be very small. In fact, if you increase the window, let's say 10 or 12, it almost becomes a plagiarism detector, right? Because then you really have the original sentence that you might even consider is copyrighted by somebody with a large N. So because then what you are indexing is really the large parts of the document themselves. And indeed, there will be a very small posting list, because if you take an entire sentence from, I don't know, Shakespeare or the ETH website, it's unlikely that it will be anywhere else in the world, except if it's a citation or quotation of this, right? So this remark is absolutely correct. And then the other remark, cannot find 2 words. Do you mean that it would be difficult to answer a query that has 2 words? Is it what you meant? And then when you say, unless you keep it, I assume you mean unless you keep the byword index. Do I understand correctly? Yeah, absolutely. So indeed, it will be tougher to query 2 words with a 6-word index, but not impossible. It wouldn't be impossible. You could still find a trick. For example, you could find all the sextuples of terms that have the first 2 terms matching your query, right? You could do that sort of things. But the problem you will hit is what happens at the end of the document, right? If these are the last 2 terms of the document, then you might have an issue. So you will find you will need tricks to do that, to solve that. And you're also correct that in that case, you might want to keep the byword index. Indices are not mutually exclusive. Just because you build an index does not mean you cannot build another index. You can build as many indices as you'd like, right? And you can have them coexist and then pick the right index depending on the query. But you need to just be aware that an index has a cost. It has a cost to store and to maintain when you grow the collection, right? All right, very, very good. So all your remarks are absolutely correct. Okay, so that was the byword index, or the k-word index if you want to use higher values for k. All right. Okay, then let's go to the other one. Precisely for this reason, actually, that there are limits to k-word indices. So let's go to the positional index. So what is a positional index? A positional index looks like this. You basically still have the list of word semantics, But right here, you don't just have the document ID, you actually have the list of the positions. So help here is at position 1. So you have a 1 here. What we put, so this is the document ID, C. In that case, C is the document ID. Here I put what is called the term frequency. I'll come back to term frequencies, document frequencies later, but just like we had at the beginning of the postings lists, the total size of the postings list, here we also like to put the total number of occurrences, the total number of positions in there, right? So here we have 1 occurrence at position 1, right? That's called the positional posting. The postings we had before are called non-positional postings. It's just the fact that a term occurs in the document. Here it's a positional posting here because it's one specific position of help in that document. Then ETH, position 2, Zurich at position 3. And here that's interesting too, is here, here, and here. So it's at position 4, position 7, and position 11. 3 times in total, right? So this is why I put a 3 here. So you see, this is a positional posting, this is a positional posting, and this is a positional posting. Okay, then we have flexibly and so on, and we continue. So now, in order to answer a query like ETH Zurich, then you see it's like we would have done with the original standard inverted index. We take these 2 posting lists, we intersect them, but after intersecting them, now we have extra information. We have extra information because once we have noticed that document C is in both, we can look at the positions in there. And here we see we have 2 here and 3 here. So there's a distance of +1 here, 2 + 1, 3. So you see, we know that Zurich is right after ETH because of that, right? So of course, in that case, there's only one position and 1 position, right? But you can absolutely imagine how you generalize it. If you have a list of positions here and a list of positions there, it's just a variation of the intersection algorithm for posting list, except that now you're looking at a positions list. Right? Okay. This actually concludes the part on actually chapter 2, so term vocabulary and posting lists. So now you know 2 more indices, you know byword indices or keyword indices, and you know positional indices. And we have done a list of word semantics. Before we had set of word semantics, now we came back to a list of word semantics for these 2 indices. All right, this is actually it for this part. We are going to soon move to the next one. Do we have any questions before I conclude this part of the lecture? Anybody? Zoom, in the lecture hall?
And none in the lecture hall so far. And I can't see any in Zoom either.
All right, so let's leave it at that. Let's stop here. And I'll see you in just a few seconds on the other side of the slides.